Okay, so we've got a couple more people that have yet to join. Make sure we have that set, and then we'll go over the where you can find the peer evaluations, because I made that pretty easy for you guys. So let's just see how many people we still have left. We have quite a few. We have at least 6 more that we should be waiting on. And I'll get set up.
Professor, I'm sorry, I don't know if you covered this. Do we do peer evaluations for our own group as well, or just for other groups?
Just for other groups.
Okay.
We'll go. I'm gonna wait for more people to join. We'll give people a couple of minutes.
Okay.
And you guys aren't supposed to start till 12:45 anyway, so we got plenty of time.
Okay, just curious. Thank you.
No problem. Last month of the year. Goodbye 2020. So let's see. We have Can I sort this? So give people just 2 more minutes before we get started, and make sure that people can present. So Matthew and Jaco and Joseph, I think that you guys are going to present using Zoom here. You don't have it because I didn't get a video from you guys?
Yes, sir.
Okay. Let me see if I can. Can you try sharing your screen right now, Matthew?
Yeah.
See if that works. I think it's
Yeah, I think I'll be fine.
Okay, good.
Oh. Is the
That's working.
okay, do you see like what am I trying to say? The Zoom
It's fine. This is fine. Don't worry about it.
Okay.
So now I need to No, let's not do that. This is always frustrating. Okay, that was just for a second so that I could share my screen back. Stealing control from you for just a minute. All right, so before we go too much further, the thing I'd like you guys to do if you're not presenting today is to go onto Blackboard, and I will share my screen and show you what we are, what you should be able to see. So you should be able to see my Blackboard screen as a student. And if you go to quizzes, peer evaluation, then you'll see you have two groups to evaluate. The first one that will present is group 6. That's Matthew, Jaco's, and Joseph's group. And then group 3, which is Fola's, Martin's, and Lane's group. So before the end of today, preferably while you're watching their presentations, go ahead and do these. They're very simple. just a couple of rating questions and then some comments or questions that you can provide to the group. They're not a big deal. So yeah, just make sure that you do those, please. Otherwise, your group presentation your portion of your presentation score will not be included. So you have to do those. Otherwise, you won't get your peer portion of your evaluation for your project. So make sure you do those for every other group except for your own, because, well, you'll have their feedback, not your own. But before we go too much further, I need to see who we're missing, because we're still missing 4 or 5 students, which is a shame. All right, so just to make sure that I've got, oh, there's, that one's incorrect. Canales, Orlando, I don't see them. Edmund, are you here? I don't see Edmund. Kittitz, I don't see Kittitz either. Alexander, Perez, and Claria. Those are the people that I don't have here. So if you're here, please speak up right now.
I'm here.
Ah, thank you very much. I'm sorry I missed your name. So that's still Alexander, Kittitz, Edmund, and Canales. All right. So then group 6 gets to start first, and each of you should be able to present as soon as I flip this switch back. And we will have them present for 15 minutes. When you have 1 minute left, I'll chime in and say, hey, you've got 1 minute to go. And then just wrap it up. After that, questions from everyone in our Zoom room, and then questions from me. And that'll be that. So if you want to get started, Matthew, or whoever, I'm sorry, whoever's starting in your first.
No, I'm the one who's going to be sharing the screen. So.
And in your feedback to your students, sorry, to your co-students, please be generous. It's been a really tough semester for everyone. It's been a tough 2020 for everyone, and 2021 is going to start out just the same way. So I'm sure all of you are aware of how difficult it is to work in a group, especially when we're distanced this way. So please, just remember that and be generous in your evaluations and in your questions and comments, because we do want to show that we're interested in what your groups are doing, because I am, and I really hope that they turned out well. So with that, I will let Matthew take the stage.
All right.
Let me mute myself. I apologize for this. Johnny, you got to stop with the blender. I'm sorry. All right.
Poor Johnny.
Okay. I'm sorry about that.
All right.
It's quite all right. It's a good start. Very 2020.
All right. Take it away, Jacob.
All right. Good afternoon, class. So today I'm with Matthew Clark, Joseph Green, and myself, Jake O'Nackville. And our project is called Let's Take a Theoretical Selfie. Next. So our objectives and motivation. Originally, we set out to create a camera driver for a Raspberry Pi camera module in order to show our classmates who we are and what we look like. We were going to do this by reverse engineering the driver that comes pre-installed with the Raspberry Pi OS. However, our original objective did not address the issue that we encountered during the implementation of this project. First problem arose shortly after our first progress report, when we realized reverse engineering the original device driver was impossible due to the fact that it was a closed source. In addition to that, developing a device driver from scratch for a camera module is much easier said than done. This opened our eyes to the complexity of the V4L2 framework, which we'll get to later. Thus, the evaluation is theoretical. Next slide. So on the left side, so the left picture, is the Raspberry Pi when we set it up using a television as a monitor, and connected to it is connected to the PC via remote desktop software. And the software we used was VNC Viewer. And on the right picture is the Raspberry Pi with the camera module. And I'll let Joseph take the hardware introduction.
Let me unmute myself. So at the beginning of our project, we, like Jaco said, we wanted to create essentially take a picture so that we could show all of our, our classmates what we look like and who we are. And part of that was deciding what hardware we would use and the actual function of that hardware. Specifically, how does a camera module work? I didn't know before I started this endeavor, neither did my group mates. So part of my job was kind of figuring out how that worked and what approach we were going to do to kind of address how that was going, how that interacted with the driver that we wanted initially to create or reverse engineer. So a camera hardware handles light and converts it into information in the form of electricity through the use of a camera sensor. I'll kind of do more of a deep dive into how the sensor actually works in the next slide. But essentially, the device drivers handle that information. And part of our problem was, unfortunately, a lot of that information is handled on the GPU side of our Raspberry Pi, which unfortunately is a closed source, and we're not able to really take a look at it in any of the research that we found. And so then from the GPU, it gets sent to our device, which our device drivers then handle that information, and then we can use, and then the Raspberry Pi actually can layer APIs on top of that device driver to manipulate that image. Next slide. So, so for our hardware, a camera sensor is essentially like a matrix of tiny sensors that detect photons and have a rolling counter of how many photons come in contact with them. And this is important because of the camera sensor that we actually use is closer to a video camera than it actually is like a DSLR, meaning it has that rolling photon counter. So when an image wants to be taken, a few things need to happen. First, all the counters need to be reset, and then once the counters are reset, a time later, those each line needs to be read to the frame. So I kind of go through this in these pictures. So if you look at the top left picture, this is what happens right when you turn the camera on. The sensors start at 0, obviously, and this is the matrix that I was talking about, the matrix of sensors. This is a very simplified explanation of what this is, but this is where our data actually comes from. So the next image to the right of that, image is what happens when you want to start actually take an image or take a frame from those elements. A reset starts to go down, which you can see the RST in the center here, starts to go down and resets each line back to 0. So in there you can see the top line is 1 because the reset just hit that, and then the rest are rolling and constantly counting, so there's actually ahead of where the reset is. The third image, you can see that it is now starting to read those lines into the frame as the reset goes on. So in this case, because only the line read 3, all the 3s head over, and so on as the reset continues to go down. And the last image, you can see that it's starting to fill out and populate that frame. Next slide. So where does the Linux, where does our operating system actually come into play here? It's actually really interesting because of the way the frame works. Because Linux is not a real-time operating system, all of that time frame between the reset and the actual reading of each line is a pre-configured speed, and that is just configured into the GPU, and then that it reads each line and then it sends it to the Raspberry Pi. So the CPU is running Linux actually doesn't, like I said earlier, doesn't actually communicate with the camera directly, but rather the GPU communicates to the GPU, and then the GPU communicates to the actual camera module. Unfortunately, I alluded to earlier, everything that happens on the GPU side is closed source. There's information out there about what happens, but not necessarily the code for us to break down and see how every exception is handled. The GPU assembles all those lines and actually does the buffering and the post-processing on that frame image, such as noise cancellation and color correction all happens on the GPU side, and then it gets moved over to the CPU once it's finished with that process. Next slide.
Those device drivers that Joseph spoke about are part of the V4L2 framework. For simplicity purposes, we'll call it L2 for short. For those who don't know, that the Raspbian OS is based on the Debian GNU Linux and optimized for the Raspberry Pi hardware. Therefore, the camera module we implemented uses the L2 or V4L2. The V4L2 framework defines which API the Linux camera driver supports in order to be V4L2 compliant. The Linux kernel uses this camera driver to initialize the hardware and produce video frames. Each of these functions has a specific implication to the camera sensor. Often, the driver interacts with the camera sensor, receiver, chip, or FPGA by reading and writing I2C or SPI registers. Next slide. Next slide. All right. So all drivers, well, first let's understand the V4L2 framework. So all drivers must have the following structure. A struct for each device instance containing the device state, a way of initializing and commanding sub-devices, if any, creating V4L2 device nodes, such as DV VideoX, DV VBIX, DV RadioX, and keeping track of device node specific data. It also has to file handle specific structs and contain per handle data. And it has to be able to do video buffer handling. So each device instance is represented by a structured V412 device, and you must register the device by calling this line of code, which is V412 device register parentheses DV V412 underscore DV. And in that code, I'll break it down for you. So DEV is the pointer to the struct device. The MDEV is the pointer to the struct media device, and it may be null. The subdev is a struct used to keep track of the register subdevs. The spin lock is for locking the struct. It can be used by the driver as well as if the struct is embedded into a larger struct. The name refers to a unique device name, by default, the driver name and the bus ID. Notify. Here's a notify function called by some subdevices. The control handler, if the pointer to the control handler struct, and it may be null. And the prio, it refers to the device priority state. The ref is used to keep track of the references to the struct, and release, which is finally, we have the release function that is called when the ref goes to a 0. And next slide, and I'll hand that to Matt.
Okay, thank you, Jacob. So this is with initializing and commanding subdevices. So each subdevice driver must have a v4l2 subdev struct. This struct can be a standalone for simple subdevices, or it might be embedded in a larger struct if more state information needs to be stored. And that's a common theme you'll see. Next is creating L2 device nodes. So the actual device nodes in the dev directory are created using the video device struct. This struct can either be allocated dynamically or embedded in a larger struct. To allocate it, we use the command struct video underscore device pointing to my dev. For file handle specific structs, struct v4l2-fh provides a way to easily keep file hand specific data that is used by the L2 framework. Struct v4l2-fh is allocated as part of the driver's own file handle structure, and file pointing to private data is set to it in the driver's open function by the driver. In many cases, the struct v4l2-fh will be embedded in a larger structure. In that case, this is what the call would be. And lastly, for video buffer handling. So the video buff layer functions as sort of a glue between a L2 driver and user space. It handles the allocation and management of buffers for the storage of video frames. There is a set of functions which can be used to implement many of the standard POSIX IO system calls, including read, pull, and mmap. Another set of functions can be used to implement the bulk of the L2 IO control calls related to streaming IO, including buffer allocation, queuing, dequeuing, and streaming control. Using video buff imposes a few design decisions on the driver author, but the payback comes in the form of reduced code in the driver and a consistent implementation of the L2 user space API. So moving on to implementation. Well, to put it simply, we have not seemed to find success in implementing our own portion of the L2 API upon the Pi. Why? Well, despite the API being open source, the driver modules developed with it are not. So without any solid referencing to the camera module drivers, our hopes are dim. But despite this, we will continue to attempt until the final report is due. And that is it. So we'll open it up for questions.
Do you want to? Thank you very much. Would you guys stop sharing your screen that other people can chime in? So, are there any questions from the class?
I just wanted to say that I thought, can you guys hear me?
Yep.
Yeah.
I I say you guys did a really good job. I just wanted to say that because like your presentation was very good and like your um you guys clearly like understand what was going on. Um, I was just saying so when you guys were talking about the some of the modules weren't being open, like what was exactly open source and what wasn't?
Okay, so the way the camera, I guess for this purpose, just the camera module, like, is connected to the Raspberry Pi. That's just kind of like a simple way of putting it. The API used to do that is what I've mentioned like a bunch of times, the V4L2, which stands for Video for Linux API. And that's open source. But in this case, and I think with other Linux or like anything that's using a Linux operating system, the actual drivers developed with that API are closed sourced, and that's what we found. Does that make sense?
Yeah, I got you.
So it's like the API, that's information that can be used by anybody. The API is like the like the functions that are predefined, some of the structures that are predefined, and like what was done with that to create like the actual driver was done by like a third party in this case.
So it'd be like you guys kind of have to like work blind in that sense. Like you guys wouldn't be able to. It'd be like really hard to like find documentation on that.
Yeah, I can allude more. Even the like preloaded the Raspbian as an OS, when you buy Raspberry Pis, the OS that you get with it, it has other like camera APIs as well on it that I found. And the problem with those is like those are all in Python and I can see what those are, but I can't see any of the data, like how that data is created, essentially.
Right.
And so that's kind of where the problem comes in. Is like I don't really I know where the data comes from. Like there's diagrams that show me where the data comes from, but I don't really know what it is or how it's created or how it's like, like maybe like even the importance of it really. Well, that's not true. I can know the importance, but like within those APIs, you just kind of can manipulate that data, i.e. like the image itself. So like I could change, like the gain or like the ISO, but I don't really know what that does, It's just a function that I call.
Anybody else?
Cameron, you're speaking, but we can't hear you.
Sorry, I forgot. I double muted myself to be safe. How is your cameras connected to your Pi? Like, are you using just a straight USB connection to it, or is it like going through the GPIO pins on the actual Pi?
The GPIO.
Yep.
Okay.
Any other from the class? So I have a couple of questions. There's the first is you mentioned that the driver for your particular camera module is closed source. Is that because of the camera model that you chose, or is that for all models that would use the GPIO pins or whatever interface that you have connected to it?
That was just happened to be, I guess, for the model we chose.
Yeah, after, sorry, go ahead.
But from what I saw, like we went with like the standard route, if that makes sense.
You went for a commonly used route, right?
Yes.
But were you able to find later on? Did you find other cameras that did have open source drivers?
Well, one of the things I actually looked into was something called libcamera, which in that case is open source. And I did try to configure that to our Raspberry Pi. You had to like download several packages, and then in one of the configuration files, you had to do a little bit of changing. But the Pi itself like couldn't handle what was it? I can't think of the term I'm looking for, but
So
like
the,
after downloading all the packages, we had to.
yeah, my question is more towards the heart. You have a piece of hardware that has closed source drivers on Linux. So you weren't able to inspect those. Did you look for other cameras that did have an open source implementation of their driver on Linux is my question.
No, we did not.
Okay.
Yeah, not before purchase. Like, yeah.
Well, I mean,
purchased,
afterwards it would have been an option to see, okay, well, if there is an open source camera driver, can I take a look at that one?
Mhm.
So one of the things I don't quite understand, maybe because I'm not that familiar with Raspberry Pis, is why the GPU is involved in camera control or in buffering. So can you explain a little bit more why the GPU has to be involved here?
That is just part of the framework with, at least with the given the Raspbian. That's with part of the initial, like the framework when it is distributed by the manufacturer. Like, and so when you plug in using those the pins on the board, that's just where it's handled. I don't know why that is per se. I just know that that's from all the forum pages that I've read. It's like, this is how it is, and that's kind of I can't particularly say why they chose to do it that way and why it's closed source.
Yeah, I mean, it's surprising because it's just a device that has its input pins and its output pins.
Mhm.
That could be controlled by any general purpose processor.
Mhm.
So why the GPU has to be involved is an interesting question that I was hoping you had the answer to.
No, I can look more into it so that we can include it in our final report. Make sure to make a note of it.
So the last piece is, I don't quite understand from your presentation the connection between the V42L and what the GPU is delivering. How does a device, how does this device present it? How does it, there's some kind of connection that I don't quite get. What is V4L providing? And how does the camera interface with it? Those are the two things that I'm not quite clear on from the presentation.
This is how I kind of understood it, and at the same time, I could be wrong. And I hope this answers your question. So when maybe a picture is taken, and input/output request is put on, and then that's like, as what Joseph had went over, that's converted into electrical signals, which is, I guess, handled first by the GPU. And the next part of handling that are those V4L2 device drivers.
So there's still what does V4L provide? What is the purpose of it?
It's an API
That
that's what the drivers are created with.
So then you have a device driver, and that provides what services?
Handling the, I guess, the raw data from the input/output device.
So we have a camera.
Yep.
And V42L is going to communicate with the camera. Now that's what I understand you're saying.
Yep.
So then that's the boundary between the kernel and the device. What services then does V42L provide on the other side?
So what do you exactly mean by services?
So you have a device over here. That's
Yes.
camera,
Yes.
and the kernel's talking to it for some reason. Why is it talking to it? What is it providing on the other side? So we have the device talking to the kernel. Now, what is our kernel provide?
Like in terms of like user application.
What I don't know what I don't know what that service layer is. That's what I'm asking. I'm trying to get that. I'm trying to see what that service layer is. What are the services that it provides?
I guess I don't know.
So that makes it sort of
Yeah.
challenging to understand why we're talking about V42L. Like, why do we need it? Why is it part of the presentation? Why is it there?
It's the framework for the camera module that
Yeah, but
we
the
happen to
framework.
use. And the framework, from my understanding, right, it's the V4L2 API, which is used to create the drivers, which, and in this case, they just labeled it all the same thing. So you have the V4L2 API used to create the V4L2 driver, which handles the information from the camera module.
So what? Yeah, but what do we do with that information? That's the
Well, then
question.
it's, I guess, passed on to a user application.
And but in what way? Like how would I then, if I'm writing a user application, how would I get information out of that driver? How am I going to take that final step of the camera has data on it, the driver has some access to that information? How does the user then get the information out of the camera through the driver?
And process, or you could say IPC between
But
the driver and whatever user process is being used.
so I'm asking about, do you know anything about that layer, about that mechanism for communicating that information out?
I guess not. I guess not. I thought I did.
So yeah, like if we were talking about a hard drive, the driver would provide the backend for, say, an open call, right? I want to open a file.
Yeah.
That would translate to, or write is easier. If I'm going to write to a file, the operating system through the file system tracks where on the disk that sector that needs to be written. And so the device driver takes that write request and translates that to a sector on the disk to write to. So that's what I was just,
Okay.
that's the piece that that's the last piece of how do we evaluate
Yeah.
that all this stuff is working together.
No, that's something I missed. So you got me with that one.
It wasn't it wasn't meant to be a gotcha. It's I don't know about this. I don't know about V4L2. I don't know about it. I've never programmed in it. So I was just curious. Okay, well, thank you very much. Let's everybody thank the group. I appreciate the presentation and your efforts. Thank you.
Okay, thank you.
All right, so we have Cassidy, Fulla, and Lane. That's CFL. That's their group. So make sure that you guys have your evaluation, your peer evaluations up, and do those for group 6, please. And you'll have to get those in tonight. If you do them now, it's a little bit better. So just take a minute. I'm actually going to take just 1 second while you guys get set up, if you don't mind, Fulla, and I will chime in on audio when I get right back.
Got you.
So yeah, I'm sorry. While I'm doing this, why don't you guys make sure that you do your evaluations for the first group first, and that way we don't have to worry about it. So are you guys all set, or do you need a minute still?
I'm good.
Let's
think we're good.
let's give people a couple minutes to get back or finish their peer evaluation. So why don't you just get started at 1:15 right on time, and then we'll go from there.
1:15.
Yeah. So 3 minutes.
Are we good to go now?
Yeah, go ahead.
Okay. All right. Good afternoon, everyone. We're group CFL consisting of Cassidy, Fola, and myself, Lane. And today we'll be presenting our project, the SFL Storage Device Driver Interface. Our goal with this project was to use the Oracle VM VirtualBox and the Linux operating system to develop a simple device driver for a USB storage device. This would allow the computer to interact with a storage device plugged into the physical machine. The virtual Linux operating system is running on. In addition, the computer will be able to read and write files to the storage device.
So our device driver interacts with the operating system by allowing the storage device to communicate with the computer's operating system. The driver allows the computer to send and receive data to and from the USB storage device. And without the device driver, you wouldn't be able to properly use the functions of your storage device. You wouldn't be able to communicate with it once you plugged it in. It would just be plugged in and no functions would work.
All right, our motivation behind choosing to develop a device driver for our project was to challenge ourselves to get more hands-on experience with lower level development using a virtual machine. In the process, we would get a better understanding of operating systems, C programming, and deepen our understanding of the relationship between device drivers and operating systems. And because of our current circumstances, all of our meetings were held over Discord at times that were most convenient for each of our members. Due to the inconsistent nature of our meetings, each member was given more specific roles and tasks within the group. So Cassidy was responsible for organizing our meetings, researching additional information on device drivers, documentation, and coding. Fola was responsible for coding and honestly for a significant portion of our initial research that we got on device drivers that would be used to get us to our current working driver. I was also responsible for some coding and for a large portion of our documentation. I also was heavily involved in debugging errors that Cassidy and Fola encountered. So generally, we shared a lot of the same tasks, but we made up for each other's issues, wherever that may be.
Okay, so our components for our project was just basically just 2 files, which was just one make file and one C file. We called it the Tesla drive, aptly named after our beloved professor, Dr. Tesla. And the make file was, when you run it, it was supposed to create a bunch of files. Mainly, our main focus was the KO file. That file was what we would insert into the module. And also the C file would just contain all the functions and structs that you would need to have a working driver.
Okay, so in our implementation of our Tesla Drive.c, we use the built-in USB subsystem in Linux to build our own USB device driver. We had a file called the testdrive.init function in our C file that was responsible for connecting our storage device to the operating system, so the kernel. And we had read and write functions that were responsible for transferring data to the storage device using SCSI standards. So the SCSI standards we use, they're called Small Computer System Interface. It's a set of standards for connecting and transferring data between a computer and the IO device or the storage device. During the communication between the OS and the storage device, our device driver acted as the SCSI initiator. In the process of transferring the data to the storage device, the SCSI initiator is the endpoint that initiates a SCSI session, meaning that it's the one that sends the SCSI commands. The storage device acts as a SCSI target that receives and processes the SCSI commands. The SCSI target waits for the initiator command and then provides required data transfer. And then we have a module device table. The device table is a structure that was used to determine which USB devices we will be able to communicate with the device driver. We had IDs in there like the vendor ID and the device ID. This comprises of all the IDs to device, and when an ID matches the module, it loads and initializes. The probe function was our main function. It performed checks on the information passed to the device and decided whether the driver is really appropriate for the storage device. It initialized hardware, allocated resources, and registered the storage device with the kernel as a block.
Can you hear me? Sorry, cut out for a second. Okay, so we also had a called the test exit function. This function would basically tell what the kernel tell the kernel to deregister the module, and we had the test init function, which would initialize the module to the kernel and register it. We had a disconnect function. This function was to basically just tells the kernel to output whatever message you want when the device has been disconnected. And we had a USB driver struct. This is a bus driver. From what we understand, it's basically just a block of code that initiates all the functions and structs that you'll end up needing in the driver. one of our issues that we did come up with was with default drivers being used by the kernel. So when we ran make, it would create our own KO file, and we would insert it to the module, but there would already be one running already. So what we had to do was, because the VirtualBox already had a device using that module, the default one was called the USB storage. We had to blacklist it, which we'll highlight in the next slide. But that's basically what the summing up what we implemented.
So here's some of the issues. We encountered a lot of small scale issues that took some time to resolve. Early on, we ran into compilation errors while getting more familiar with creating a makefile for the module, such as syntactic errors. Like, I think at one point I spent like 2 hours trying to figure out why it wouldn't compile. It was because there was an unnecessary space in the folder name, which was really infuriating to find out. So that resolved that, but we also ran into issues after compilation, realizing that default USB storage drivers were interfering with the new one. So we had to research how to prevent this, and we later learned how to blacklist the default USB storage driver, which would allow our new driver to interact with the device.
So as you can see on the side here, there is this is a read-only file that you can find in the kernel's files, and we had to like edit it using Vim so that we can just add this little line of code on the bottom where it says blacklist USB storage. This should just prevent the kernel from using the default one, since we couldn't remove it.
And then our final major issue was getting the driver to read and write to the storage device, which will be discussed in greater detail on the next slide by Cassidy.
Okay, so as I said earlier, to do the read and write functions and the general data transfer, we have to use the SCSI protocol. And in order to use the SCSI protocol, we needed to find a document that contained the right SCSI commands that we needed to incorporate in our read function, our write function, and in the data file that we intended to transfer. Now, we were able to write a basic read and write function, but it wasn't the proper one that was able to work for our storage device. And yeah, this resulted we weren't able to transfer the data. So the read function was responsible for transferring the data from the storage device, and the write function was responsible for transferring the data to the storage device. And by not having the proper SCSI commands in these functions and in the data file, we were not able to transfer data to and from the storage device.
Okay, so I pre-recorded a demonstration of just what happens when we insert our module. Hopefully you can hear it. Just let me know if you can't. But hello and welcome to our demonstration portion of our video. Let's start off by listing out all the modules that are currently running on this kernel. So we hit lsmod. As you can see, there is no USB module anywhere. There is a default one that we had to blacklist. So let's run our own. If we run our make file, it should create a bunch of files that our module will need to run on the kernel. Yep. And our main focus is this testerdrive.ko file. If we insert that module, we should be able to see it come up. Okay. Now, if we all the kernel messages, we should see that it registered a new driver called the tester drive. And then if we list out the modules again. So here in the video, I forgot to note this. I just kind of highlighted, but as you can see, like on the top right there, it says tester drive. So that's the module that is we just installed onto the kernel, and then that's really it for now. Sorry, it's a little rough, but when we I'll just skip to the part where we remove and or add and remove a USB to it. And if we print out the kernel messages again, show us right here that our device has been plugged in. The tester USB drive has been plugged in. And when we take that out, print out the kernel messages one more time. We should see right here it says that the tester drive has disconnected. Hello and welcome. Okay, so then we just had a list of all of our sources. So our first source was basically just it had a bulk of a lot of the information. It was actually very detailed. That went to a lot of stuff that's just a lot of extra stuff that went to just writing drivers in general. We had 2 playlists that were basically tutorials on just writing basic modules and stuff like that. So that's where a lot of our background knowledge came from. Our second to last source was just our USB, like how to blacklist modules that we didn't want running. And also our last one was just about all the information about the SCSI stuff. So that's it for our project, and we'll take any questions now.
Very nice. Are there any classmates that have questions first? Start there. Oh, looks like Fulla's internet is being Fulla's internet. Oh, he's back.
Hello?
Yep, there you are. How about the class? Are there any questions for the group from the class? Okay, well, if you guys are going to give me the floor, I'm going to ask a couple because I'm very interested. The first, I want to talk about what you're calling SCSI. That's typically pronounced SCSI. So the SCSI standard is a standard. So but you mentioned that you weren't able to meet the standard or use the standard. Can you go a little bit more in depth on why?
Okay, so we found out that that was a way that we could transfer data specifically to USB storage devices, but we weren't not able to find the appropriate commands, like specific commands that we had to incorporate in our code to use. We found resources that said that it is used to build our read and write functions, which are responsible for transferring data to and from the storage device, but we were not able to find what commands or what pieces of code we were supposed to use to implement. It was just a broad understanding when we research that it's supposed to be used in the read and write functions and in the documents that we want to transfer, but we couldn't find any more information on it.
But SCSI is an open standard produced by ANSI, the American National Standards Institute. that's available. So that document is available. So when you say commands, what do you mean by commands there? You say
So
you didn't know the commands to read and write information from your USB device.
yeah, so so what I gained from our research is our commands were just different type lines of code, different, they were different lines of code that we need to use, like logical LUNS, loons, like logical unit numbers, and that we need to use in our read and write functions, our read and write operations, and we couldn't find a proper the proper loons to use in those functions to process the data transfer.
So LUNs are no, they're basically an array element. They refer to, it's the equivalent of a sector. So, then there's an implementation. There are several implementations of SCSI, at least one in the Linux kernel that you can use. So the piecing those two together, what the connection you just didn't seem to make that connection, and it's right there. It's sitting right there. So that's unfortunate. Can one of you take me through your source and sort of trace how a write request would come in and then how it would be sent to the USB stick, if you have your source available?
Let me see if I can pull it up. All right, let me see if I can share my screen. Can you hear me still?
Yep.
Hello, can you hear me?
Yeah, and I can now.
Okay, I'm sorry.
It's
Okay.
okay.
So, sorry, where am I at? So we have uh our two functions. Yes, okay. So we have our two functions right here. It's basically like you said, it does kind of function like a an array. So we have our it's like in an integer array that the USB will try to copy from the user like when it's reading, and then it'll let me try to explain.
So start from here. So line 85, how does that get invoked? What does that mean when we enter this function? What's going on?
So I'm not sure entirely.
Did one of you guys write this?
So this what we implemented after taking it out. Like this is like something we added in like before our presentation
But
to
who
provide
wrote this?
documentation. So we were sourcing this. This is more like we try to implement this with our own project, but this isn't like what we actually like wrote really. We were really responsible for like the other aspects of the project. This is something like we tried to implement like kind of last minute to try to figure it out, but we actually didn't actually implement it.
So who wrote this code? Lines 85 through 98.
I wrote it to try to, we included the source that we got it from, and I wrote it to try to attempt to figure out myself how to use the SCSI, how to
So
use.
Can you walk me through this function, Cassidy, and tell me what it's trying to do?
This does not really implement the oh, sorry. Okay, this does not really implement using the protocols that we needed. This was just like a regular read and write. So what it does basically, it's just like the bones of what the read and write is supposed to be without it fully being
Sure.
implemented. So this was to get the message line 88, I think, was to get the message from the file that we're trying to send. So as you can see in 85, the struct file F, it was supposed to be the it's coming from the data file that we're using, that we're trying to transfer to the storage device. So this is supposed to get the the bulk message from the file. Line 88 is supposed to get the bulk message from the file and see if this was compatible to transfer over the kernel using our device driver. And line 89 was just our if statement to see that if this did work, then we would be able to transfer the file. And if it didn't, it printed out the negative e-fault error to the kernel to let it know, like, it's to not make the device driver as a whole crash, to just make sure like it's a error that is printed out to know like the data transfer didn't work, basically. And this is just allocating a certain block of memory kind of, and the whole line 88, it's just going out in the message, and then it's in the whole thing, like when it says USB bulk message, that's the whole message, and then it's just elements of the message throughout that whole line 88, saying like which device it's going to, what's the message, that's how it's interacting with the kernel, and the size of the message and so forth. And then it's similar to the write function, which is below, but the write function has a little bit more detail because the write function is actually writing stuff to the USB device. So, and the read function is actually like transferring the data from the USB device. So the write function is basically the same thing, but just a little bit more.
Okay, well, thank you. Are there any other questions from the class? All right, well then let's thank group 3. Thank you guys very much.
Thank you.
Nice presentation.
Thank you.
So make sure to do your peer evaluations for group 3, please. Please do them earlier rather than later because they'll close tonight. So make sure you get those in today. And we will see everybody on Thursday for the next set of presentations. So thank you guys again, and thank you for your hard work throughout the semester. I really appreciate it.
Thanks, Professor.
Have a good day.
Thank you. Thank
See you
you.
Thursday.
See you.